Thank you very much for the invitation. It's a great pleasure to present with such a great lineup of speakers today. Today I'm going to speak about graphs of convex sets, which is this new optimization framework for discrete continuous decision making that I've worked over the last few years. This is the outline of my presentation. I will start with some motivation and goals. Then I will describe what these graphs of convex sets, GCS, are, and what kind of optimization problems we can formulate over GCS. Then I will present a unified optimization method for solving GCS-related problems. And then I will go through a variety of robotics applications. So as a motivation, I don't think I have to convince this audience about the importance of optimization in robotics and about the fact that many of the problems that we need to solve on a daily basis in robotics involve a mix of discrete and continuous decisions to be optimized jointly. If you take, for example, a standard collision-free motion planning problem, you have discrete decisions that come from collision avoidance constraints. For example, if your UAV or quadrotor is facing a tree, it needs to decide whether to avoid the tree on the left or on the right. That's a Boolean discrete decision that is tightly coupled with the continuous trajectory of the center of mass of the quadrotor. In robot manipulation, you often have coupling between logical decisions. For example, do I use a tool to reach an object that might be too far from the body of the robot? And these discrete decisions are again coupled with the continuous decisions, which come from the continuous position of the objects we manipulate. In locomotion, making and breaking contacts, we have seen this in many presentations already, are discrete decisions that are coupled with the trajectory of the joints and the center of mass of the robot. And even in more kind of warehouse automation settings, you often have problems of moving objects as fast as possible, and there the discrete components comes from selecting objects and deciding where in which bin to place them. And the continuous component, again, comes from the continuous trajectory optimization, typically minimum time problems. So the goal of my research has been to try to develop a modeling and computational framework to deal with these discrete continuous optimization problems. And if I were to kind of list the three essential characteristics or properties that such a framework should have, I would say that first of all, it should be expressive and essential. Expressive in the sense that it should kind of nicely capture the interplay between the discrete and the continuous parts of our problems, and essential in the sense that it should lead to kind of simple mathematical optimization problems that we can formally study the complexity, for example. Then it needs to be fast and reliable, and this can be done by leveraging many tools that we have from combinatorial and convex optimization. In particular, I feel that the field of combinatorial optimization has many deep results that have not been fully kind of embraced by the robotics community and the planning community. And finally, it needs to be high level and easy to use, as we cannot expect all the users of our frameworks to be experts in optimization and know which parameter they have to tweak in order to see desired results. We need to provide some high-level interface that is kind of shields the users from all the technicalities that run behind the scenes. I won't even try to kind of list all the different directions in which this interplay between this discrete and continuous decision-making has been kind of tackled. A few relevant to us in robotics are, for example, task and motion planning that provides very scalable and effective methods for these kind of hierarchical planning problems. On the other hand, seen from the kind of perspective of the three criteria that I just listed, task and motion planning does not really lead to a increased mathematical formulation of the problem that we can study formally. And also, it doesn't really fully exploit all the optimization tools that we have. Many speakers today spoke about nonlinear programming approaches to problems involving also some sort of discrete decision-making, for example, complementarity constraints. This can be very effective in some cases. However, in the general case, they are often not reliable enough for deployment in the real world. And also, I don't feel that they are the best tool that we have to deal with kind of intricate combinatorial optimization problems. Finally, mixed integer optimization is kind of the natural language to think about optimization problems with discrete and continuous components, but on the other hand is extremely low level. And for whom of you have played with these mixed integer solvers, you need to understand a lot of what is going on behind the scenes in order to design efficient mixed integer programs. So the goal of today is kind of to design mixed integer programs that are good in some sense by construction. So what we propose as a framework for blending discrete and continuous decision making is this idea of graphs of convex sets, which I'll explain next. I'm sure that everybody in this room is familiar with weighted graphs, ordinary weighted graphs. We have a set of vertices V and a set of edges E. Every vertex V is paired with a scalar cost CD, which is a real number that represents the cost or weight of the vertex. And similarly, for the edges, we have a scalar cost. A GCS is a generalization of a weighted graph where the weights or costs associated with the vertices and edges are not scalar anymore, but depend on the underlying continuous variables that are paired with the vertices on the graph. So in particular, every vertex V in a GCS is paired with a convex optimization problem, which is defined by three things: a set of variables, xv, here, a convex constraint set, calligraphic xv, and a convex cost function that, given the value of the variable xv associated with the vertex, returns the weight of the vertex itself. So this is not a fixed number anymore, but is a convex function of an underlying continuous variable. Similarly, on every edge of a GCS, if, for example, we have an edge that connects a vertex V to a vertex W, this is going to be paired with convex constraints that relates the variables, the continuous variables of vertex V and vertex W, as well as with a convex cost function that, again, even xv and xw returns the weight of the edge. So this is kind of a nice data structure. What kind of optimization problems can we formulate over a GCS? And the response is that any optimization problem that can be formulated over an ordinary weighted graph can be formulated over a graph of convex sets. For example, take the shortest path problem. In the discrete version, we have a source vertex and a target vertex, and we look for a path of minimum cumulative weight that brings it from the source to the target. This is a purely discrete combinatorial problem where we want to find the best path among a finite set of paths. In the GCS version, we have a discrete continuous problem where we are still looking for a discrete path through the graph. But depending on the path that we take through the graph, we activate some of these convex problems. And we need to choose the variables corresponding to these convex problems in order to have the to compute the cost of the path we have selected. So these two choices are tightly coupled: the choice of the underlying continuous variables together with the choice of the high-level path through the graph. We need to optimize them simultaneously. And of course, there are other classical problems, essentially any classical problem in graph theory, traveling salesman, minimum spanning tree, but also matching problems or facility location problems. They all have kind of natural GCS extension. So if we try to be a bit more formal, the discrete problem on the top row, it can be described as follows. We have a set calligraphic H, where essentially we list all the admissible subgraphs that we can select from. In the shortest path problem, these are all the paths from source to target. In the traveling salesman problem, they are all the cycles that visit all the vertices in the graph, etc., etc. Among these subgraphs, these admissible subgraphs, we want to select one of minimum cost, where the cost of the subgraph is simply the sum of the costs of the vertices and the edges in the subgraph. Okay, the GCS generalization of the problem I just described is similar, but now we have this interplay between the discrete choice of the subgraph and the continuous variable. In particular, we are still selecting a subgraph H within a list of admissible subgraphs. Depending on the choice that we make for the subgraph, in particular for its vertices and edges, we activate a sequence of convex constraints, one per vertex and edge in the subgraph. The cost of the subgraph is again the sum of the cost of the vertices and edges, but this time these are convex functions instead of just scalars. Okay, so the problem on the top is kind of well known, and we know how to solve them. The question we're going to pose next is how can we efficiently solve the problem at the bottom, the discrete continuous version. And we propose kind of a unified method for solving these GCS optimization problems using mixed integer optimization. So just to set the expectations, most of the GCS problems that we care about are NP-hard, unfortunately. If you take, for example, the shortest path problem, which is in the ordinary version with non-negative weights, is solvable in polynomial time, its GCS extension turns out to be NP-hard. This essentially means that we cannot expect to be able to formulate these GCS problems exactly as convex optimization problems. What is, in some sense, the next best thing that we can try to do is to formulate them as mixed integer convex programs. A mixed integer convex program is an optimization problem where we have an objective function g, which is convex, some constraints c represented by the set c that are also convex. Part of the variables are real, so continuous, and part of the variables are integer. So this model the discrete part of our problem. This is a non-convex problem just because some of the variables are integer, right? Otherwise, everything is nice and convex. Why MICPs are in some way a good class of optimization problems? Well, because using enumeration techniques like branch and bound, they can always be solved to global optimality, provided that a solution exists. And also they can be efficient in some cases. This kind of exhaustive enumeration can sometimes be instead pretty efficient. And the things that make a mixed integer program efficient are essentially two. The first is obvious. The problem needs to be compact, meaning that it must have few variables and constraints. And the other thing that is fundamental is that the formulation is quote unquote strong, which means that the convex relaxation, which is the convex program that we obtain by just throwing away the constraint that part of the variables are integer. If this convex relaxation is a good approximation of the original problem, then our branch and bound algorithms will run very quickly. In many cases, we can even skip the branch and bound directly and solve the problem directly from the convex relaxation, if the problem has some special structure. So just a couple of quick highlights on how we construct our mixed integer convex program that models the GCS problem. The starting point is the formulation of a discrete graph problem, the one here on the top left, as an integer linear program. So the one here on the top left is the problem over the ordinary weighted graph, the purely discrete combinatorial problem, where we were looking for a subgraph of minimum cost. We can reformulate this as an optimization problem with binary variables, 0, 1 variables. In particular, the variables in these optimization problems, y, are going to be the incidence vector of the subgraph we select. So this vector y has one entry for every vertex in the graph and for every edge in the graph. And the role of these binary variables is to take unit value if and only if the corresponding vertex or edge is selected in the subgraph. Then we need to enforce some constraints on the possible values that these incidence vectors can take. And these typically have the form of a polytope, so a set of linear inequalities that this incidence vector must satisfy. And this polytope essentially separates the incidence vectors that correspond to admissible subgraphs, paths, tours, etc., to the incidence vectors of subgraphs that are not admissible for our problem. The objective simply multiplies the scalar cost by the corresponding binary. So when the binary is 1, we pay the cost of the vertex or edge that we included in the subgraph. When the binary is 0, we don't pay anything. And let me say that many people in robotics get scared when you say mixed integer programming, and so on. These are extremely efficient integer programs. We have been studying for like 60 years. There are books of thousands of pages that study them very deeply from a mathematical point of view. These integer programs can solve gigantic optimization problems in a fraction of a second. So don't be scared by the word integer. Sometimes this stuff can be very efficient. So now that we have a kind of a nice binary encoding of the choice of our subgraph, the next question is how can we use these binary variables that come from the discrete problem to kind of activate and deactivate the convex pieces of our GCS problem. So in this pictorial form, we have our GCS. We have selected a subgraph using binary variables, and we would like only the corresponding convex sets and functions to be kind of enforced, right, using these binary variables. And there is a nice solution also to this problem using homogenization operators or perspective functions. They are the same thing, essentially. I'm just going to show you an example. I will consider just the convex constraint associated with one of the vertices of the GCS, but the same idea applies to all the edges and all the functions, etc., etc. So this is actually a cool trick that I wish somebody told me years ago, and it's kind of broadly applicable. Imagine that you have a variable xb that needs to belong to a convex set if a binary variable is 1, or otherwise, if the binary is 0, you don't want to enforce any constraint, right? A simple way of writing this constraint is to multiply the convex constraint by the binary variable. On the left, we have the product of a binary and a vector. On the right, we have the product of a binary and a convex set. When the binary is 1, on the left-hand side, we have the vector xb, and on the right, we have scalar 1 times set. That's the set itself, so we have our original constraint. When the binary is 0, on the left-hand side, we get a vector of zeros. On the right-hand side, we get 0 times a convex set. That's the origin. So 0 is always in the origin, nothing. This constraint is going to be redundant. We can then add an auxiliary variable z that represents the product of y and x. And the reason why we introduce this variable is that this kind of nicely separates the convex part of the constraint, saying that a continuous variable is in the non-negative scaling of a convex set. It's a convex constraint. The non-negative scaling of a convex set is a convex cone, as kind of shown here pictorially. And this kind of isolates the non-convexity of these constraints in these product constraints, for which we have, again, decades of tools to deal with, and in particular to derive strong mixed integer formulations and convex taxation. We had to develop something special because here we really only assume convexity of our sets and not, for example, that they are described by polynomials or linear inequalities, but we essentially generalize what was there in the region. So we have to repeat this procedure for every set, convex set, and every convex function in our problem. Then we get these bilinear inequalities, which we can relax efficiently with convex combinatorial optimization techniques, and we get our mixed integer convex program. So how does our mixed integer convex program perform in terms of the compactness and strength requirements that we described before? Well, the size of our mixed integer program is linear in the size of the graph and the vertices, the convex programs of the vertices. So that's essentially as good as it gets. And the mixed integer programs have also tight relaxation, tight convex relaxation in practice. Again, these are NP-hard problems, so we cannot expect the convex relaxation to always be exact. But informally, what we notice is that if you start with an integer linear program for the discrete problem that has a tight convex relaxation, that is typically inherited by our mixed integer program for the GCS version of the problem. And I do have some bounds, but I don't want to be tedious and show you all the results. I can show you some experiments later. So let me just also highlight that none of these transformations, binary variables, is something that the user of our framework is exposed to. I've developed this library called GCSOpt in Python. It should be pretty straightforward and easy to use. You can pip install it. It's part of the CVXPy ecosystem. That means that every time that CVXPy has a new release, automatically they test it on our code. If something breaks, they let us know in advance. So your code should not break at any time. And the idea is that the user needs to start from a robotic problem, think, okay, what is the graph underlying my robotics problem? What are the continuous variables, the convex sets, the convex functions? Give us this description of the problem, then we take care of everything else automatically. So in the last few minutes, I would like to show you some applications of GCS. And GCS is, in fact, a variety of applications that go even beyond robotics and control. If we focus only on the robotics and control applications, footstep landing for humanoid robots is a problem that in my PhD lab we have worked on, and we had some mixed integer programming techniques. GCS is dramatically faster, order of magnitude faster. We can solve this problem as a shortest path problem GCS almost at control rate. Some interesting problem in computational geometry related, for example, finding minimum volume covers of triangular meshes are representable as facility locations problems in GCS. More on the control side, control of hybrid system and minimum time control of linear systems can be seen as GCS problems. And as special cases, we recover the best known mixed integer formulations for these problems. And for other problems, we even outperform the best known formulations. One application that was particularly interesting and successful for us is motion planning. And this is also naturally formulated as a motion planning around obstacles. And this is naturally formulated as a shortest path problem in GCS. The idea here is that we want to move from an initial point to a final point with the curve of minimum length for simplicity, and we want to avoid the obstacles in red. If somebody, and we have developed good algorithms for this, gives us a convex decomposition of the free space, this can be an expensive step, but again, we have worked on it. Then there is a natural graph that we can associate with this convex decomposition, where every convex set becomes a node in our graph, and two nodes are connected if the underlying convex sets intersect. Then we can parameterize a trajectory within each convex set with 2 points, the initial and the final point of the trajectory. We can enforce on the edges of our graph of convex sets the constraint that if you move from one convex set to the next, then the final point of the first piece of trajectory needs to be equal to the first point of the second piece of trajectory. This ensures continuity of your overall path. And then you can have costs on the vertices that say every time you visit a vertex, you pay a price that is equal to the length of the trajectory segment in that set. And this kind of correctly replicates the original problem of finding a trajectory of minimum length. And this can also be generalized to design a smooth trajectories using Bezier curves and polynomials. To kind of show off and show kind of the effectiveness of this motion planning tool, we thought, okay, what is the most non-convex optimization problem, motion planning problem that we can come up with? Let's traverse a maze with a path of minimum Euclidean length. There are standard mixed integer formulations for a problem like this, and if you want to be precise with those, you need the number of binary variables that is equal to the number of cells in the maze, and then, you need the number of trajectory pieces that is equal to the number of cells in the maze, and then you need the binary variable to assign every trajectory piece to potentially every cell in the maze. So you get something like 6 million binary variables for this problem. And the convex relaxation, after you solve this convex program with 6 million variables, then you go straight to the goal, which is kind of silly, right? Our GCS formulation has a number of binary variables that only grows with the number of cells, so it's linear instead of quadratic in the number of cells. In this case, we had about 7,000 variables, and the convex relaxation for this problem is exact. In less than a second, you solve a convex program, a second-order con program, where you allow the binary variables to be non-zero or non-one, but at optimality, they're either 0 or 1. That is a mathematical proof of global optimality of the solution that came from the convex optimization problem. So here we really leveraged the kind of graphical structure of the problem, the network flow formulation. If one really tries to understand what's going on, why this convex relaxation is tight, there are some explanations, but at least for me at first sight, this was a surprising result. We tried this on more interesting robotics problem. This is a drone flying through randomly generated environments, minimum time trajectories in 3 dimensions. Then we can reconstruct the orientation using differential flatness. In this case, we just solve the convex relaxation and we apply a cheap rounding that for this specific class of problems is guaranteed to lead to a feasible solution. And we study on the top right the tightness of the relaxation across the instances. 50% of the instances have a convex relaxation that is perfectly tight. And even in the worst case, the gap between the optimal solution and the convex relaxation is at most 20%. And even better, if you take the convex relaxation and you do some cheap rounding, it's a randomized depth-first search in the graph. 95% of the time, you recover the global optimum through just the convex program and some cheap rounding after it. And the worst case gap with respect to the global optimum is like 2-something%. This applies also to higher dimensional problems. Here you have 2 robot arms that are completing non-trivial motion planning problems. Here we are planning the trajectories in the 14-dimensional space of the joint configuration space of the 2 robots. Needless to say, decomposing this 14-dimensional space into convex sets is a complex issue. And again, we have worked very hard. Alex and Pete are here around summer. They have developed great tools for this. But then when we have this convex decomposition, we can just solve the convex relaxation and it finds this kind of very non-obvious trajectories, again, through only the solution of the convex program. In this last example, we were both optimizing the trajectory of the robots, the order and the timing at which, for example, the mags are picked in place. That's a pretty trivial motion planning problem. Finally, we have also applied, this is a work by Bernard, another student that was in my PhD group, GCS for non-prehensile manipulation. Here we have a standard kind of pusher slider system. The idea here is that different mode sequences represent different paths in your graph of convex sets. And with every vertex of the GCS, you associate kind of the dynamics of the system in a fixed contact mode. That's a nonlinear dynamics. We can approximate it using semi-definite relaxation. This gives you an overall relaxation of the problem. But again, you solve the convex relaxation, you do some rounding, and you obtain the trajectory shown on the left, which before they told me, I would have been surprised to know that these are generated using convex optimization, right? They are very contact-rich and involve some non-trivial thinking about the geometry. So in conclusion, how does GCS perform in terms of the 3 kind of requirements that we had at the beginning? Expressive and essential, fast and reliable, high level and easy to use. Well, I think it's not perfect, but it does a pretty good job in every direction. I think, I hope I convinced you that it can model interesting problems in robotics, and it leads to clean mathematical formulations that we can really study formally. It leverages powerful tools from combinatorial optimization, especially. We kind of inherit everything that is known in combinatorial optimization about the integer programming formulations of these graph problems. Kind of by design, everything is transmitted to our mixed integer programs. And it's kind of easy to use, to the point that some of the students in the undergraduate classes and class I'm teaching, they manage to solve non-trivial problems with this. You still need to know what's a convex function, what's a convex set. Many of them try to force non-convex functions and complain about errors. That happens, so it's not really completely super high level, but I think that especially with the software that we have designed, it's kind of easily accessible. Thank you very much for your attention. I would like to leave you the QR code for the code. And on the right are some papers that you might be interested in reading if you like this presentation. Thank you so much.